Well, hello there, everyone. Let's talk electricity today. Electricity is the final unit that we have, and there's so much cool stuff to do. I'm going to put everything down to circuits from the basics all the way to circuits in this one video. So we're going to have quite a bit going on here. If you need to fast forward through parts of it so that you have okay, I'm a little bit off here. I guess the board needs some recalibration, so maybe some of my words are going to get a little bit mixed, not perfectly lined up, but we'll have to deal. My point was, what I was going to say is if there's something very, very specific, let me give you an idea. The first thing I'm going to do is go over electricity in terms of voltage, current, resistance, a little bit about power, a little bit about batteries, actually probably batteries, then power, and then into circuits. Start with series, move to parallel, and then finish with a combination circuit. So considering that's the sequence I'm going to go in, if you have something very specific, you can fast forward until you think you're about where you need to be. All right, but we're going to start with the how and the why a little bit. All right, we're going to start with this idea of charges moving in a circuit. Okay, so the electricity seems magical a little bit because you can't see it much. You can't really see anything. You can see the effects and so forth. But the whole idea is that we're going to take an electric charge and we're going to force it to move through a pathway and actually drop energy off somewhere where that energy can be changed into something useful, such as a light or a doorbell or a motor or something along those lines. So we have to get those charges to move around in a circuit. So the first thing you have to figure is like, why would they move around in a circuit? Why would they move in the first place? And the reason for that is that they get pushed. Okay, and we're going to use the analogy of energy just a little bit. The reason for that is because it's similar, but energy and potential energy, kinetic energy, and so on is something that's actually we have a pretty decent idea about. So let's say that's a boulder, and we want to get it here, where it has all sorts of potential energy due to its height. Well, we know if it's at rest, we're going to have to push it, and we're going to have to do work on that object to make it get up the hill, because otherwise it's just going to stay right there and it's never going to go anywhere. It's never going to move. So we apply a force over a distance and we push it up the hill, and then it has gained potential energy because of its position. Okay, now let's take that and make it into something we can't really see, which would be our charge. So if you figure, let's say this is a test charge and it's positive. Right? If you have another charge that's also positive, these naturally want to repel each other because they're similar charges. So if you want to get it to go this way, you're going to have to do work. And as you build up and you get closer and closer, you would notice it's harder and harder to push it closer. Think of like two very strong repelling magnets, right? You're going to have to put a lot more force in there to get it to get close. And the minute you let it go, it's going to go flying the other way, right? So when you do this, you are storing energy. It's another type of stored energy, but it's actually an electric. It's actually an electric potential energy. We can't really see it, but we know that that's what would happen. So the idea is instead of a gravitational potential energy, we're dealing with an electric potential energy because it's these charges instead. Now, that sounds like a great place to begin mathematically, but the problem is it doesn't take some things into account. It doesn't take into account how big is this charge and how big is this charge and, things along those lines. We need something that's a little more of a ratio because let's face it, if this is small and this is small, it's not as much work. But if this is big and this is small, we need something standardized. Okay, so what we do is we have a way to describe that, and it is called electric. Well, we have several names for it. Electric potential is one name. That's not even the most common name, but that's a name that MOPS likes to use. The common name is voltage. It's also known as potential difference. Man, this thing off being off center is going to bother me. I can tell. Or it's otherwise known as a potential drop. So we have four names. Okay, that's not even spelled correctly. What in the hidey ho is that all about? All right, let's try that again. That's what I get for talking and writing at the same time. all of these refer to the same darn thing. Now, voltage is definitely the most common name for it, but they are all equal to something. Okay, so what they are equal to is the amount of electric potential energy, and we're going to divide it by the amount of charge that we have. Okay, so we're gonna make a ratio out of it depending upon how much charge there is. So the volt, which is our unit, let's look at it from a unit perspective first. The volt is actually joules per coulomb. Coulomb is the unit of charge. If I want to put this in symbols, I would say delta E divided by Q. Q is the symbol for the coulomb. Okay, so there what we're looking at is the idea of what the heck actually is voltage and what does it do. And why does that voltage move in the first place? Because it gets pushed, and we said, well, actually, let me change color here a little bit. So let's take this and talk about that a little bit more. What is pushing these things around? Right, that's what the battery does. So the function of a battery is to provide a push or provide energy to the charges, right? It provides the voltage. It provides this. Now, if we're talking about something that's like a dry cell battery, you know, like AA, AAA, 9-volt, even your car battery, whatever, those are actually fixed, and it's based upon the chemicals that are involved in the battery themselves. And when those batteries go dead, as we like to call it, it's not because they run out of this. It's not because they run out of charge. Charge is really a function of the number of electrons that you have, and everything has electrons. What it means is that you run out of chemicals inside the battery. So when we talk about things like rechargeable batteries, they are a misnomer. Okay, but the real definition is probably too much to put on a package, and most people wouldn't understand it. But you, as a physics student, you are expected to understand that the battery does not run out of charge. It does not recharge. It does not make electrons. What it does, if you recharge a battery, what you're really doing is you're remaking the chemicals that go into the battery. It's a reversible chemical reaction. So that is something important that you should recognize. They remake those chemicals. And yeah, the charge, when it goes through the battery, it picks up extra energy. I like to think of it as like the charge has a backpack on it. And so it goes through the battery, it puts energy in the backpack, wanders out, heads around the circuit, and then drops that energy off at different resistors until it comes back to the battery with an empty backpack. So the charge never gets used up, per se. It drops off its energy, but it does not drop off, you know, it doesn't actually lose anything else. Okay, so our battery actually is really, really important. If you're just plugging something into the wall, that's like having a battery that never runs out, right? Because the energy company is providing that push on those electrons. That's what ComEd's function is. All right, so that is a very quick description of voltage. Definitely check your notes. I know we did a little bit more when it came to voltage. All right, so what are some of our other terms that we're going to take a quick look at? I think I'm going to go to blue. I'm feeling bluesy. All right, so how fast does the charge move? Woof. Way at the top of the screen, I can barely reach it, and I went sideways. Who knew? Okay, so how fast does the charge move? Okay, first of all, individual charges, they move really slow, so don't be fooled. Right, if you're talking about, you know, this charge right here at the light switch having to make its way all the way through the circuit to the light fixture, it's going to take hours. All right, individually, they move very, very slow. I say consider it like you're trying to walk down the hallway with the freshman who can't figure anything out. It takes a while, okay? However, the circuit starts to move all together at the same time. So when you turn on a light switch, it's instantaneous light. That's because the electron, the charge that was like sitting right next to the filament in the light, poof, it gets knocked into place and da-da, it lights up. So individually they're slow, but collectively we're looking at how fast does it move, and that gives us what we want in terms of, you know, light, sound, etc. That gives that to us instantaneously. The rate of the charge flow is what we call the current. Okay, the current is the speed of charge flow in a circuit. And you know that term circuit, I've already tossed it around a couple times. All a circuit really means is you have a complete pathway for those charges to move. They don't just stop at a dead end. They make it from a battery all the way around some loop and get back to the battery. That's all a circuit is. And if you open it or you break the circuit or you short circuit something, you're interrupting that pathway. That's all that's talking about. Now current, this is the stuff that's dangerous. This is what will kill you. The symbol for current, unlike the V for voltage, is I. I don't know why they do that, they just do. The unit is the amp. The amp is a very large unit. We also have milliamps and microamps, which is, you know, what we did in our lab where you actually had to measure stuff, all right, and do some converting. Lots of our measurements are really in these smaller units because it's easier to say that than say something like, you know, 1 times 10 to the negative fourth amps. So they say something like, you know, 10 milliamps instead. It makes it a little easier. Okay, so this is the speed of the charge. It is measured in amps. The symbol is I. And then the last one, resistance. This is measured in ohms, right, which is a lambda. Ooh, that's a pretty good one. I never usually do those all that well, but what do you know? All right, so this is the restriction of electron motion. So if you are, you know, if you just put a bunch of batteries around and attach it to, or you grab a battery and you put a bunch of wires around that battery, well, yeah, it's going to move around. It's going to move really, really fast. It's going to get really, really hot. And it's probably either going to melt or go on fire, or you're just going to waste all that energy. Everything just gets really hot. The resistance, we're not considering the wires to have resistance. In reality, they do. However, we're going to pretend that they don't. All right, we are just talking about little devices that we put in our circuit to take that energy and do something useful with it. Okay, that's what we're talking about when we talk about resistance. So again, light bulbs are a big one, buzzers or doorbells or motors or something like that. Whatever, your cell phone, any object that you're going to then take that electrical energy and use it for something else. That's what a resistor is. And energy just gets dropped off at the resistor because then it will transform into something else. Like I said, we ignore the wires, but we do look at all of these things. Now, the relationship between the three pieces is called Ohm's law. V equals I times R. We use that often, okay? Something else to consider, we do have some conversion factors for electrons and coulombs. All right, 1.6 times 10 to the negative 19th coulombs. So if you are being asked about charges, you have to really be careful and look and see, am I being asked about electrons or am I being asked about coulombs? They're different, but they are, like you can convert one to the other, but they refer to the same basic thing, but they're not the same item. So you have to make sure you're dealing with the proper unit when you look at those. I do believe, let me just check real quick here. Oh, I did leave myself some space. I'm so smart. The idea of power. I'm going to give us a little bit of space on that as well. All right, so V equals IR is incredibly important. We use that completely when we are doing our circuit conversions. We also use this conversion of electrons to coulombs quite often. All right, so our last big topic that we spent time on was the idea of power. Okay, so luckily I have given myself an entire blank slide to look at there. Okay, so the idea of a circuit is an energy transformation tool, right? So we have this energy, it's coming from the battery, it's being delivered someplace, right? It's being delivered to what's called the load or the resistor. And so this is not current, but this is also a speed, all right? It's a rate. So this idea of power. How fast is energy delivered? That's really the question of what, power. How fast is that energy delivered? The more power you have, the faster that energy is being delivered. The less power you have, the slower it is. So if you consider, we did power, the idea of power when we were talking about energy, and we said it was the amount of work being done over time. All right, the work being done. And work, just like energy, is measured in joules. Well, that's funny. We have something, we're dealing with energy as well. So when we deal with this in terms of electricity, we're going to say it's the change in energy, right? How much energy did we lose as we went along? And then, of course, time is measured in seconds. So it's the amount of, well, actually, what am I doing here? Let's just put that back with a T, right? So if we're going to put this in terms of units, it would be joules per second. All right. So let's remember that. Let's see if I can get this to erase carefully. All right, close enough. At least you know there's supposed to not be something there, right? So power is still measured in a watt. The unit is still the watt, but that is small. So we often use the kilowatt, which is, there's 1,000 watts in a kilowatt. All right. Now, let's see there. We got some other possibilities too, though. We've got some, based on VIR and what we know about power, we actually have several iterations of this particular formula. We can take it and we can move things around and come up with other important relationships that will find us power. So here's another really important one. If you take the current times the voltage, you will find the power. These last two are ones that I don't use very often, but you never know. You might find them handy sometime. All right, power is also equal to V squared over R. And again, that's just manipulating the definition for current, the definition for voltage, and Ohm's law, and you get all four of these relationships. But like I said, this one and this one, these are the ones you're going to see the most. Also, what you're going to see with power is the idea of an energy calculation, like how much does it cost? Like let's say, for example, you have a 60-watt light bulb and you run it for 10 hours. You leave it on and it costs, I don't know, 5 cents per kilowatt hour. And you want to know how much are they going to charge me on the electric bill if I leave that light bulb on for 10 hours? Okay, so energy calculations, you're going to see these in MOPS quite a bit. They're not that hard to do, right? But if you think about what ComEd is doing, right? So if we say power equals change in energy over time, and all right, let's get the time out of the bottom, multiply both sides by T, right? Time, okay, that's, you notice they're using hours, right? And power, oh, watts, okay, got that over there. That will tell me energy, how much energy I'm being used. And if you ever look at some of the, like Mobil or ComEd, whatever they say, Exelon or something like Exelon, an energy company. Energy, yeah, energy. They charge you for the amount of energy you use. So you can see here, I'm doing that. I'm looking at power being multiplied by time. So typically what we would say then is a watt times a second. But power companies actually change the units because watts are tiny and seconds are tiny, and they don't want to print all those zeros on their bills. They also don't want people to have a heart attack when they open their bills. Oh my God, we used 8 billion, watts per second of energy. Oh my gosh, we got to turn all the lights off and never ever turn them on again. And they probably don't want that either. So they're using much larger units, the kilowatt and the hour. Okay, so when you do calculations like this, sorry, that's not supposed to be an equal sign. We'll just make it a big arrow. All right, we're going to change watts to kilowatts by dividing by 1,000. We're going to change seconds to hours if it's not already changed. As you can see in this question, I already did that for you. All right, but then we're going to multiply the power times the time, and that will give us the amount of energy that we use. And then we can figure out how much it costs. So watch how this works. All right, so 60 watts equals 0.060 kilowatts, right? Because I divide by 1,000, right? So I did that. Next, I've got 10 hours. So what I'm going to do is multiply those two together, right? Because power times time gives me energy. So I'm going to say, okay, 0.060 kilowatts multiplied by 10 hours. Well, I just moved the decimal place again, so I get 0.6 kilowatt hours. And notice I put a dot there. I didn't put a division. It's not a ratio. It's a multiplication. So that's how much energy I've used. All right, that's my energy. Now, how much does it cost me to use that energy? Let's figure that out. So 0.6 kilowatt hours, and it costs me, what did I say, 5 cents? So I'm gonna leave this in terms of cents. 5 cents for every 1 kilowatt hour. So when I multiply those two together, I'm going to get 3, right? Hopefully, I'm not using my calculator. I know that that's 30 and I move the decimal over. So I should get 3 cents. It should cost me 3 pennies to run that light bulb for 10 hours. It's actually pretty cheap, right? See, usually it's not the energy costs, it's the taxes and stuff that get you, but you know, that's a lesson in civics. But now you get the idea here. Be careful when you do these. They're not tough, but watch out for the unit on the money. Often it's in dollars, or we think, oh, it's so small, I must need to divide by 100 and put it in dollars. Be careful. Watch what the question is asking. All right, so a few practice problems in some different areas that we're dealing with here, just to kind of give you an idea of some of the things you can do. So I'm going to reach around here and grab my calculator, and let's get ready to solve a few of these. All right, so as you can see, I'm being given electrons and time, and I want to know current. Okay, so current, by definition, what is current? It's the amount of charge moving in a given period of time. So electrons, that is not charge. That's a type of, it is a charge, but it's not in the proper unit. I need that Q to be in coulombs. So I am going to use this conversion factor to help me out. All right, so let's start there. 7.45 times 10 to the 17th electrons. This looks a lot like what you did in chemistry, right? You need those units to drop out. You need coulombs on the top. So 1 electron is 1.6 times 10 to the negative 19th. Now you can multiply these two numbers together. You're going to get a small number, but it's not going to be nearly as small as something to the negative 19th, right? So 7.45 times 10 to the 17th, and I'm going to multiply that by. You'd think I'd have it all worked out, but I don't. I just have my calculator here. Okay, so when I do this, I get 0.1192 coulombs. If you do this on your calculator and you do not get that, chances are it's because you're entering the value incorrectly on your calculator. You want to use the double E button to put the exponent in. So I actually typed in 7.45. I accessed this button and then I hit 17. All right, so if you're not familiar on how to enter in scientific notation, please find me and ask. All right, so now, oh, I almost walked away from the question. I'm not quite done. This is how many coulombs I have, right? 0.1192. I want to divide it by 0.810 seconds, and that will give me my current. So I get a current of 0.147 amps. That's the current. All right, that's a pretty typical problem. Just when you're dealing with electrons or coulombs, watch the units that you're working with and check your formulas before you go too far. All right, here's another one. All right, 9-volt battery. Okay, so I've obviously been given voltage. It's attached to a circuit. And oh, look, here I am back at electrons again. How much energy is drained from the battery? Okay, so voltage. By definition, right, what are we looking for? We're looking for the change in energy per charge per coulomb. All right, again, I'm not given coulombs. I am given the 9 volts. I'm going to move the Q over here because you make far fewer algebra mistakes when you don't have a fraction. So if I take the Q out of the bottom, okay, I got to take the charge and multiply it by the volts. Well, I have the volts. I just need the value for the charge, right? It's not 4.5 times 10 to the 18th because that's electrons. We want this in coulombs. So 4.5 times 10 to the 18th electrons. Same sort of conversion I was doing before, right? 1 electron is 1.6 times 10 to the negative 19th coulombs. So let's see if I can type this in correctly the first time I go to do it. 0.5, 18. All right. So I get 0.72 coulombs. Let's see if I can fit that in here. I can. Woohoo! All right, this will give me my delta E. And so let's times that by 9. And I get 6.48 joules is the unit for energy. And there you go. All right. Now, this one is a classic VIR. Let's take a look. All right, 22 ohms, that's resistance. 120 volts, that's voltage. How much current did it draw? Oh gosh, so simple. I love VIR calculations. They're some of my favorites just because it's so easy, right? So if I want to figure out the current, I'll just divide. We've got 120 volts. We've got 22 ohms. Let's do some quick math. Now, 5.45 amps. To be fair, 5.45 amps is way, way too much. That'll probably set something on fire in your house. More about that later. Okay, now we're going to start looking at circuits and actually understanding circuits. The whole idea of a circuit is you've got that complete pathway for those electrons, but you also have advantages and disadvantages to different types of circuits. This is what's known as a series circuit. And a series circuit is where you have one path for the charges. So let's say that this is the high energy end. When a charge goes around, it's going to go across this one, then it has to go across this one, then it has to go across this one, and then it has to go back to the battery. All right, there's only one way for everything to go here. It is not, you know, oh, willy-nilly, let's go wandering off in a different path. You have to go in a certain direction here for a series circuit. So series circuits have some mathematical rules to go along with them. All right, a couple of advantages here. They're very hard to overload. They tend never to cause a fire, but they have some distinct disadvantages as well. Since I only have one pathway, if I interrupt it anywhere, whether it's, you know, I put a switch here and I open up a switch, or uh-oh, my light bulb went out over here, it doesn't matter. I lose them all. So these are like the cheap Christmas lights that you get, you know. If one bulb goes out, the whole strand goes out, and you spend quite a bit of time trying to like figure out which one it is, that's a nightmare. Be smart and buy the more expensive lights because they don't have these kind of circuits every place. Okay, but mathematically they're relatively easy to understand. What you always want to do is find what's known as the equivalent resistance, or RT. And when it comes to series, it's really simple because you just add them up. Right? So we've got 4 plus 3 plus 5, so 7 plus 5 is 12. So in this case, my total resistance for the circuit is 12 ohms. Once I know my total resistance, I know my total voltage, because that's the battery, is 6 volts. Find the total current. Total current is going to, well, let's see, VIR. So I'm going to do voltage over resistance will give me the current, right? So if I do 6 volts over 12, that's going to give me a half an amp. After you figure out the totals for each of these, your next job is to figure out what's the value for the current and the voltage across each of the individual resistors. And this is usually where folks get a little bit squiggly, especially if they don't know what kind of circuit they're dealing with. With a series circuit, the current is the same everywhere. It's the voltage that splits, and it's exactly the opposite for a parallel circuit. So what you do is memorize one of them, and then you know them both, right? Because if you know one, you can figure out the rest. So if the current is the same, the next thing I'm going to do is I'm going to label everything that I know, and that would be the current. If the current stays the same, that means that all of these are half an amp. And now I have 2 out of the 3 pieces. I can use VIR and figure out the voltage, right? So 5 ohms times half an amp is going to be 2.5 volts. Half an amp times 3 ohms is going to be 1.5 volts. Half an amp times this one, 4 ohms, is going to be 2 volts. And you'll notice the 2 plus the 1.5 plus the 2.5 adds up to 6, as it should, because it splits. It doesn't split evenly, but it splits. So here's how it really works going around a battery. Like, let's say you're a charge and you leave here. You've got 6 volts of energy at this point. All right, once you go through this resistor, you drop 2 of those volts. That's why it's sometimes called potential drop. You have 4 volts going here into the next resistor. right? And then you lose another 1.5. So it's that 3, 2.5. That leaves you 2.5 volts going from here to here. And then, oh, look, the 2.5 volts get dropped here. You have no more volts left going through. Now, it's not that you used up the charge, but what you did is you used up the energy on those charges. That's why the charge has to go back to the battery and pick more energy up. All right, that's a little bit different than what you would think. Okay, so the current, the flow, it never slows down because the charges are using up that energy. That stays the same. That's based on the resistors that you have, but the energy that they're carrying around with them get dropped off at each of the independent resistors. So that's something to keep in mind. Now, our next one is called a parallel circuit, and parallel circuit rules are a little bit different. All right, a parallel circuit, let me pick a different color here. No, I want to pick something that's not on the screen. All right, so let's say you're a charge and you go here. Well, at this point, you can go here or here or here. You've got multiple choices, really. Not that they sit there and hem and haw about what direction to go, but there's more than one pathway. They have to pick one, and then the charges eventually come out. Obviously, it goes like this and like this and like this, and comes out and then heads back to the battery. Okay, so what happens in a parallel battery, if I lose this one, let's say, the other two still, the electrons still have a path to go. So these are the better Christmas lights. These are the ones when one thing goes out, they don't all go out, because that would be a nightmare. Especially, like, imagine if your house was wired as a series circuit. What a mess that would be, right? Because the light goes out in the living room and you lose the refrigerator. That would be crazy. You don't want to do that. Okay, so how do you solve these? Well, the rules are a little bit different. The resistance rules are inverses. So you actually have to do fractions. So I'm not saying you can't do them on your calculator as decimals, but you do have to remember that when you add these three up, you're not getting the answer. You're getting 1 over the answer, and you have to flip it over using the x to the -1 button on your calculator. Okay? So 1 over RT in this case is going to be 1 on 13 plus 1 on 4 plus 1 on 28. And unless you are a math genius or Mr. Hartz or Mr. Hearn or Mr. Chagreau, I don't think you can do all those fractions just easily in your head. I don't know if they can either, but I sure as heck can't. So I'm going to use my calculator. I'm going to put my fractions in parentheses. All right, so I'm doing 1 divided by 13 plus 1 divided by 4 plus 1 divided by 28. And when I get that and I do that math, here's what my calculator tells me, 0.362. Now that's not resistance. That is 1 over the resistance. I have to do x to the -1, and I get RT equals 2.76 ohms. Now, a couple of things you should notice here. 2.76 ohms is lower than any of the branches that I have. Any of them. And if I added a fourth branch, guess what? That number would drop. It would be less than 2.76. These are the types of circuits that can cause fire. You can overload them. That's why we have circuit breakers in our house, to make sure that we don't do that. Okay, so what happens here is the resistance overall is dropping, and that is eventually going to lead to a current rise when you go through the circuit. So if you have more current, that means you have more heat and you have more chance of a fire. These can be dangerous if you put too many together. So you never want to like put a whole bunch of extenders on the same plug. I mean, one is fine, but putting multiple extenders on there, that's dangerous. So watch out for stuff like that. Okay, so we've got our total resistance. Let me switch colors because green is not my jam. Let's pick something different. All right, my total voltage is 120. Now let me, that was my finger. I touched the board. Whoops. All right, so now I want to do V equals IR. I'm going to find the total current. So I'm going to say 120 volts divided by 2.76 ohms. This is going to be definite fire material, 2.76. Ugh, 43 amps. That's crazy town. 43.48 amps. Okay, but now that you have the totals for your circuit, let's take a look and see what stays the same and what changes. In a parallel circuit, the voltage is the same. You get equal push across every branch. And what that means, if you're dealing with a battery that has a limited chemical supply, is that you're going to drain your battery really fast when you have something in parallel. If you're dealing with something that's, a plug in the wall, obviously that's not going to be a big deal. All right, so what I know is that all of these are going to have 120 volts because in terms of parallel, you get the same voltage for all. All right, now right here, they're actually giving me a list, so maybe I'll fill some of that in. So 2.76, my total current was 43.48. And now I'm saying that all my voltages are the same, right? We get equal push across each of the branches. So what you would do then is individually, you're going to do, you know, voltage divided by resistance gives you current for each one. So I'm going to do 120 divided by 13, and that's going to be number one. So I get 9.23 amps there. And then 120 divided by 4, well, that's 30 amps. That's insane. And then 120 divided by 28. Nope, 120 divided by 28 is going to be 4.29 amps. So that's how you would solve a parallel circuit. Now our last one is the most complicated. It's called a combination circuit, and that is the circuit that usually gives us a little bit of fits because it's kind of like, well, what am I doing here? Right? I have pieces of both, and we've definitely practiced quite a bit when it comes to breaking these down. I'm going to just label everything on here with some made up values. Let's make this one a 25 ohm, 10 ohm, 15 ohm, 15, and then we'll say 10 and 10 right here. We're going to draw multiple pictures here. Let's go over this. So the idea of doing a combination circuit is what we're going to want to do is take this circuit and draw picture upon picture upon picture. And what that's going to allow us to do is eventually simplify this circuit down to where it's one resistor, one battery, and then we'll work backwards and do all the math. Okay, it's very critical that you don't skip a step here. You have to do total resistance, total current, total voltage first. It may take a while if you're a really complicated circuit. What I see here is 1, 2, 3. 3 pictures. All right, what I'm going to do is I'm going to start with the most complicated part of the circuit, which is right here, where I have these two in parallel right there. Then I'm going to add this one to this one. Then I'm going to take these two branches and simplify them together. And then I'm going to take these two branches and simplify them together. And now I just have dots everywhere, which makes no sense to anyone. My apologies. You'll see what I mean in just a minute. Okay, so let's draw the first one. I'm just going to, it's going to seem tedious, but I'm telling you, this is how you want to do it in order to know what you're doing. And I just draw this shape first, and I do the resistors next. All right, so 120 volts here, 25 ohms, my bad. Let's try that. All right, and I've got a resistor here, I've got a resistor here, I've got a resistor here. Now, what I'm going to do, let's leave these the same. So 10 ohms, 15 ohms, 15 ohms. Okay, what I'm going to do is I'm going to take these two 10 ohm resistors and say, well, if that is a single resistor, what is the value of that resistor? Like which single resistor can I replace these other two with? And so mathematically, because the two 10 ohms are in parallel, hopefully you can tell, right? Because once you're charged and you go from here to here, you've got a choice to go here or here, up to, kind of up to the charge, what it wants to do. So that's in parallel. And so I would say 1 over 10 plus 1 over 10 is 2 over 10. And I flip it to get RT, because that's 1 over RT. So that means RT is 10 over 2, which is 5. All right, so this is an equivalent of a 5 ohm resistor being right there. Okay? Now, hopefully you can see I can, and I'm going to do this in 2 steps. I probably should do it in 1, but I'm going to do it in 1, but I probably should do it in 2. I'm going to add these two. These two are in series, and these two are in series. The lower ones are in series with each other. The upper ones are in series with each other, because once a charge goes across the top, it has to go through both. And once the charge goes across the bottom, it has to go through both. So I'm going to flip to the other page. I gave myself a blank there, but now I don't remember what I did. That's not so smart. Okay, so I need a box with, we're just going to do one in parallel on each. Okay, got it. All right, I'll still probably flip a little bit back and forth, but we'll do it like that. Right, this one was 120 volts, and of course I have absolutely no memory. Let's see if I got any of this written on a piece of paper, so I don't have to change it. Okay, this one is still 25 ohms, right? But now what we're doing is we're going to simplify that one and that one. We're going to make it into a single. So if I had a 10 and a 15 on the bottom, that's in series, I'm going to add that up to 25 ohms. And I had a 15 and a 5 on the top, so that is going to simplify to 20 ohms. So I've got two 25 ohm resistors and a 20. My next step, I'm going to take this parallel piece and I'm going to simplify that. So then it'll look like I have two of them. Right? I still have a 25 ohm resistor right there, but now it's like I have a single one here, right? These are in parallel with each other, so I have to do 1 divided by 20 plus 1 divided by 25. Actually, let's do that over here. 1 over 20 plus 1 over 25. This is going to be 1 over RT, and what I get is 0.09, and then when I take an inverse of that, I get an RT of 11.1. So I could replace these two resistors in parallel with a single 11.1 ohm resistor, and it would be the same thing. All right, my final step is to take these two series and put them together. All right, so let's do that quickly. All right, so 25 plus 11.1 is 36.1 ohms, and this is a 120 volt resistor. Okay, so now we're going to start working backwards. So our total resistance worked out to be 36.1 ohms. Our total voltage, 120 volts, and our total current, let's divide those two. Total current is 3.32 amps. Okay, we figured everything out for this one. Now what we're going to do is start taking our information, primarily our voltage and our current, and we're going to go back and figure them out one at a time. So we're going to work in reverse. All right, so this, you got to figure, let's assume like we've got a charge going this way, right? So we've got 120 volts. We've got 3.32 amps. And when I put it through this particular circuit, it is a series circuit. So the question then to ask yourself is what changes and what stays the same. In a series circuit, current stays the same. So I'm going to label these. And now I'm going to solve for the missing piece, right? If I multiply 25 times 3.32, I get 83 volts. And if I take 11.1 times 3.32, I get roughly 37 volts. I rounded, I admit it. So it may not perfectly add up to 120, but it's darned close. Oh, it does. Never mind. Haha. Okay, so this 25 ohm resistor, if you think about it, it's the same over on the next one and back here. That 25 ohm resistor is the same every single time. So let's see if I can, what did we get? 3.32 and 83. 3.32 amps and 83 volts. That's what's going on that resistor. That's not changing. End of story. So let's go back. Now all I want to do is focus here. Whoops, I went right off the board, right? That is what's going to go into that branch, right? So I care about the amps and the volts for that piece, and I'm going to apply it to the next one. Okay, so let me change colors again just to keep things funky fresh. All right, so we've got 3.32 amps and 37 volts going into a parallel circuit. What stays the same in a parallel circuit? Voltage stays the same. So 37 volts. 37 volts. Let's figure out the amps. You're going to do 37 volts divided by 25. 1.48 amps. And then 37 volts divided by 20, 1.85 amps. Okay, I have a feeling I'm going to be toggling here for a few minutes. I apologize in advance. So my top one is 1.85 and 37. 1.85 and 37. All right, 1.85 amps, 37 volts. And my bottom piece was 1.48 and 37. Okay, 1.48 and 37, 1.48 amps, 37 volts. Okay. Now, don't worry about the directions. Like, why are you going one direction for one and one direction for another? It's just about space, quite frankly. All right, at this point was where I had condensed two things into one. So I jumped a step here. I apologize for that, but well, c'est la vie. All right, so let's start with the bottom. I'll switch colors back again. All right, let's go to blue. These two right here, they are in series. What stays the same in a series? The amperage. So 1.48 amps, 1.48 amps, and then you can do the multiplication and get, resistance times amps and get the voltage. So if I multiply this by 10, I get 14.8 volts. If I take 1.48 times 15, I'm going to get 22.2 volts. Okay, when I look at the next step over, that's exactly the same. There's no change here. So I'm going to just write these in there. I figured those out over here. This one is 1.48 amps, 22.2 volts. Okay, now I'm going to do the top. The top is in series with itself. You notice they're not the same values down here and up here, right? The amps are different. The voltage is the same, but the amps are different. So make sure you carry the numbers from the proper piece. All right, these two resistors, the 15 and the 5, they are still in series. So that means, here, let's change colors for the top and the bottom. That means that the current is still what stays the same. So 1.85, I apologize how messy that is. It bugs me. But there's not a lot I can do. I'm reaching as high as I can to get that. All right, so 1.85 times 15 is, I'm going to round it, 28 volts. And then 5 times 1.85 gives me roughly 9.2. So I'm just going to say 9 volts again. It's not perfect, but it's pretty darn close. Now, if I look at that 15 ohm resistor, that's exactly the same as the 15 ohm resistor over here. So I can say, you are done. I know you are. 1.85 amps. And what did I say? 28 volts. 28 volts right here. My final thing to do is to take these values and apply them right there. Okay? That's the part that's going to be the last piece of our puzzle to tie in. I think I'm going to go back to green because that's the one color I don't have on here. Okay, so the two 10 ohm resistors are in parallel with each other. What am I going to keep the same? The voltage. And they're the same. Oh, how nice. All right, so if I take 10 and if I take 9 volts and I divide it by 10 ohms because V equals IR, I'm going to do that as a division. I'm going to get 0.9 amps here. 0.9 amps here. They split nicely, and now I'm done. Okay, so a couple of things. It's tedious to draw all these pictures. It's like, gosh, I could squish that down in my head, but I just dare you, if you're not an electrician, to go backwards in your head. It's not going to work out. You're going to mess up the voltages and stuff. You're going to look at it in the wrong order. So it is smarter for you to take the time, draw the pictures, and work deliberately backward in order to solve it. All right, so that is a very long lesson on all things electricity, but hopefully it gives you some guidelines if you needed something you were struggling with. Please come see me for help if necessary, and I will talk to you soon.